Look down at Palm Jumeirah from above, and the entire structure appears completely motionless. But the most disturbing engineering question about this artificial landmark did not begin with a massive collapse. It began with a measurement of exactly 5 millimeters. 5 millimeters is roughly the thickness of a standard pencil. For an island visible from orbit, that number sounds meaningless. But 5 millimeters is not frightening because it is a large physical distance. The dangerous question arises when one part of the reclaimed ground moves by 5 millimeters and the area right next to it does not. When two neighboring points lose alignment, something built above that ground eventually has to absorb the difference. And on one of the most expensive artificial islands ever built, the things forced to absorb that stress are hundreds of miles of underground pipes, power grids, and the foundations of ultra-luxury villas, which leads to the immediate physical question: what actually breaks first? When people imagine an island sinking, they usually picture the entire landmass slowly disappearing beneath the waves. They picture a cinematic disaster where the ocean swallows the infrastructure. But engineering failure rarely looks like a Hollywood movie. If the ground beneath a massive development begins to experience uneven movement, the first visible problem would not be the island vanishing. It would begin at a connection. Imagine a heavy underground water pipe resting across a stretch of reclaimed sand. If a localized section of that sand shifts downward while the adjacent section remains stable, the pipe is forced to bend. If a paved road crosses a transition point between two different foundation zones, that rigid surface will distort or separate. A drainage line relies on continuous geometry to move water using gravity. If its elevation changes unevenly, that geometry is compromised and the water stops flowing. These are the physical engineering consequences that make uneven ground movement so important. Sinking does not have to look like a uniform descent to cause a major problem. To understand why such an enormous development was ever built on ground capable of movement, we have to look at what was here before the concrete arrived. If you erase the villas, the hotels, and the roads from the map, you are left with the open waters of the Arabian Gulf. Palm Jumeirah is not sitting on ordinary naturally existing terrain. The landmark is constructed entirely on reclaimed land. Creating this foundation required moving millions of tons of sand and placing it precisely into the sea to form the fronds and the crescent breakwater. But when you relocate loose material, it does not immediately behave like solid rock. Think of pouring loose sand into a large glass container. If you pour it in, the sand will settle on its own over time as the grains slowly rearrange and close the empty voids between them. The engineers behind the mega project knew exactly how reclaimed ground behaves. They did not discover too late that artificial sand could settle. They knew the ground itself had to be engineered before anything else could be built. Because the engineers anticipated the problem of settlement, they decided to force the ground to settle before construction began. The reclaimed sand required extensive ground improvement to upgrade its engineering characteristics and support the infrastructure that would follow. The primary method used across the project was vibro-compaction. This process involved driving long vibratory probes deep into the newly placed sand. The intense mechanical vibration forced the loose sand grains to tightly rearrange themselves. As the empty voids between the grains were reduced, the ground became much denser. During this deliberate compaction process, the surface elevation of the sand actually dropped. The engineers were effectively making the ground sink in a controlled manner to minimize the natural settlement that would happen later. Ground improvement at the Palm projects was explicitly designed to control future settlement behavior. At this stage, it seemed like the structural challenge of building on a reclaimed artificial island had been resolved. The sand was densified and the foundation was ready. But a few years later, a set of measurements associated with the island reopened the question. In the year 2009, a highly controversial claim circulated regarding the stability of Palm Jumeirah. Based on interpretations of satellite-related measurements, reports emerged suggesting that the island was sinking. The reported average rate of this movement was approximately 5 millimeters per year. This became the second time that tiny measurement of 5 millimeters would define the story of the landmark. The claim immediately generated international attention and sparked a fierce dispute about what was actually happening beneath the properties. There was a clear narrative contradiction here. The ground had already been engineered and densified specifically because settlement was an expected physical reality. Yet measurable displacement was now being discussed publicly as a potential crisis. The developer firmly rejected the interpretation that the island was dangerously sinking. The debate revealed a fundamental misunderstanding about how artificial ground works and how engineering data is interpreted. When a tiny measurement makes headlines, it forces us to re-examine our basic assumptions about the ground beneath our feet. Was Palm Jumeirah actually undergoing a catastrophic failure, or was the public asking the wrong question about the data? To answer that, you have to understand that the measurement itself is not the conclusion. The measurement is just the clue. If you hear that an island is sinking, your brain naturally creates a very specific image. You imagine the entire landmass of Palm Jumeirah dropping perfectly evenly into the water. I think imagining the entire palm sinking evenly actually makes this story less frightening. If everything moves downward at the exact same rate, the buildings, the roads, and the underground pipes remain in the exact same relationship to one another. The truly dangerous scenario is entirely different. Imagine one localized area of the ground remains perfectly stable, while the area immediately adjacent to it moves slightly downward. Whatever connects those two areas is suddenly forced to bridge a changing gap. Engineers call this differential settlement. The Federal Highway Administration engineering guidance clearly establishes why differential movement between adjacent supports matters so much to structures and serviceability. When neighboring load-bearing elements settle at different magnitudes, it creates severe structural concerns. The danger comes from the deformation, the added internal stress, and the eventual cracking associated with that excessive displacement. The critical number is not how far the entire island moves. It is the difference between two neighboring points. That difference transforms a harmless settlement into a structural threat. To understand the physical threat of differential settlement, you have to reduce the megaproject down to ordinary everyday objects. Picture two large blocks of engineered ground sitting side by side. Now picture a rigid metal pipe resting continuously across both of them. If one block drops by a fraction of an inch, the pipe connecting them must absorb that shift. It begins to bend. You can almost hear the metallic strain as the material is forced out of its original alignment. The same physical rule applies to a concrete road joint spanning two different foundation zones. As one side drops, the rigid connection is stressed until a sharp crack forms in the surface. An underground drainage line relies on a calculated slope to carry water away. If the ground beneath it moves unevenly, that careful geometry changes, and you hear the water pool or flow backward. A foundation transition between a heavy structure and a lighter landscaped area faces the exact same structural vulnerability. The pipe does not care whether the movement sounds small. It only knows that its two ends no longer agree about where the ground is. Small vertical displacement becomes horizontal stress through a connection. When you look at the aerial image of Palm Jumeirah, it is easy to make a visual mistake. The island is shaped so perfectly that it looks like a single continuous object. But beneath the surface, that description stops being useful. The landmark is actually a dense web of overlapping physical networks. It is constructed from hundreds of miles of paved roads. It contains underground utility systems carrying water, power, and waste. It is held together by structural transitions, rigid interfaces, and coastal defense systems. There are thousands of buildings resting on different types of foundations. Each of these distinct systems interacts with the reclaimed ground differently. When the engineered sand beneath these systems experiences movement, every single joint and intersection becomes a potential failure point. What looks like one unified surface from space is physically thousands of interconnected systems forced to share the same moving ground. The landmark's apparent unity is an illusion of scale. Therefore, Each connection potentially responds differently to a shift in the sand below. Palm Jumeirah contains countless connections, making uniform behavior impossible. Just as the narrative surrounding the 5 mm measurement reached its peak, the story almost disappeared. The developer, Nikhil, firmly rejected the claim that Palm Jumeirah was dangerously sinking. They stated that they did not see the type of building damage or infrastructure failure that would be expected from serious subsidence. Then Fugro NPA, the organization associated with the satellite measurements, issued a crucial clarification. They stated that their initial findings had been taken out of context. Fugro explained that the early measured displacement was within the expected natural range for such a reclaimed structure. They also made it clear that no conclusion about a long-term sinking trend could be drawn from those early measurements alone. For a moment, it seemed like the case was closed. The measurements were normal, the developer was not seeing structural collapse, and the panic appeared unjustified. But if you look closely at that clarification, it did not say the reclaimed ground never moves. It fundamentally changed what the movement actually meant. To understand the reality of artificial ground, you have to separate three different concepts. There is movement, there is normal expected settlement, and there is catastrophic structural failure. These three things are not synonymous. A measurable movement captured by a satellite does not automatically mean a building is about to collapse. The sand was vibrating and settling precisely because the engineers forced it to, and some ongoing minor adjustment is a physical reality of reclamation. The relevant engineering question is not whether the sand moves at all. The question is at what point expected settlement stops behaving like expected settlement. You cannot determine that by looking at one isolated number from a single year. The answer is found by looking for a continuation of the movement over a long period. It is found by looking for severe unevenness across adjacent zones. It is found by observing physical consequences on the surface. A measurement of ground displacement does not inherently equal a disaster. An isolated satellite reading is just raw data until it is placed into a structural context. Movement alone is not enough to declare an emergency. The pattern of the movement is what determines its meaning. Imagine an engineering team analyzing the ground stability of a massive artificial island over time. When they detect a tiny localized movement during an initial scan, it is an interesting data point, but it is not enough to trigger an alarm. But when they return for later monitoring and discover that the movement in that specific area persists, the data becomes more interesting. If they then realize that the ground right next to it is behaving completely differently, the situation becomes actively concerning. The critical threshold is crossed when a physical interface above that ground begins responding to the uneven displacement. Once a buried pipe bends or a transition pavement cracks, the measurement is no longer just a theoretical data point on a computer screen. Now the measurement has a real physical consequence. This is how a standard infrastructure investigation unfolds in reality. It is not about finding one frightening number and assuming the worst possible outcome for the entire island. A number only becomes a significant warning when it develops a clear pattern and forces the infrastructure to physically react. When people search for evidence that a massive engineering project is failing, they usually look at the most famous structures. The audience instinctively expects to see a luxury hotel collapsing, a giant fissure opening across a residential frond, or a signature tower cracking down the middle. You have to reject that dramatic expectation. A hypothetical first clue of severe differential settlement would likely appear somewhere completely mundane. It would show up at a transition pavement where a private residential driveway meets the main public road. It would be visible at a standard expansion joint that has been stretched slightly past its design tolerance. It might be detected deep underground when the geometry of a local drainage network begins to fail. These rigid interfaces are the places where relative movement is forced to reveal itself. The first sign of a giant systemic engineering problem may appear in the least cinematic place imaginable. Failure clues do not necessarily begin at the most famous buildings. They begin exactly where the physical strain of uneven ground is concentrated. This mundane reality makes monitoring the island an incredibly detailed task. When we talk about the ground moving, a single island-wide average can actually hide the real story. A landscaped park, a paved public road, a heavy concrete villa, and a massive commercial structure do not impose the identical physical demand on the sand beneath them. Because the structural loading is completely uneven across thousands of properties, the ground response will naturally vary across different development zones. Relying on one headline number that averages the movement of the entire island is often less revealing than looking closely at the differences between locations. An average can make a highly complicated physical surface look much calmer than it really is. Engineers do not necessarily care about an overall average that smooths out all the critical variations. They care about the specific boundaries where a heavily loaded zone meets a lighter one. They care about the exact points where differential settlement is most likely to occur. This is why a generalized statistic can be so misleading when evaluating artificial ground. Local differences in settlement matter far more than a single unified statistic. A quiet average does not mean every individual pipe is perfectly stable. For an inland development, minor vertical movement primarily changes the geometry of roads and underground pipes. But on an artificial island, any change in elevation also alters the physical relationship between the land and the surrounding ocean. Being completely surrounded by water introduces an entirely different set of stakes. A 2023 engineering study examining the coastal revetment of Palm Jumeirah under future sea level and wave assumptions demonstrated this reality. The research discussed the specific structural upgrades that would be required under various modeled scenarios to maintain the coastal defenses. This peer-reviewed study does not prove that the island is currently destined to flood. It simply reinforces the fact that long-term coastal protection is itself a continuous engineering challenge. Ground elevation and coastal exposure actively interact with each other. On a normal city street, a slight drop in elevation is just a maintenance issue for the asphalt. But when you are surrounded by the sea, every millimeter of vertical movement carries an additional consequence for the physical barrier protecting the island. The ocean provides a baseline that makes even the smallest ground movement more significant. If severe localized movement were to persist over decades, the resulting failure would not look like a Hollywood disaster movie. Nothing needs to disappear into the Gulf overnight. The following sequence is a hypothetical engineering consequence, not a description of what Palm Jumeirah is currently experiencing. But this is the credible physical threat that engineers must prevent. If uneven movement persists, adjacent foundation zones are increasingly forced to respond differently. A road transition gradually loses its original alignment. A buried utility line slowly bends until it requires excavation and replacement. The calculated slope of a drainage network changes just enough to demand mechanical intervention. Rigid concrete interfaces begin to crack and require continuous patching. Different structures across the massive development increasingly fight against the shifting ground beneath them. The truly threatening scenario is not an island sinking entirely into the sea in one spectacular moment. The credible threat is a developed artificial landscape increasingly burdened by the need to compensate for movement beneath thousands of physical connections. It is a slow, relentless escalation of maintenance, where the infrastructure demands constant repair just to remain fully operational. It means the city never stops fixing the ground it stands on. It means the cost of simply keeping the roads smooth and the water flowing slowly consumes the resources of the development. So we have to ask the final, honest question about the evidence we have explored. Has that controversial measurement from 2009 actually proven that Palm Jumeirah is currently undergoing catastrophic sinking? The answer is no. The historical material simply does not establish that terrifying conclusion. The developer, Nikhil, firmly and correctly rejected the interpretation of a dangerous systemic collapse. Fugro made it explicitly clear that the early displacement data could not establish any long-term trend. We cannot take an early measurement of settling sand and project it forward as proof of an ongoing catastrophe. But dismissing the apocalypse does not mean dismissing the engineering reality. The real engineering test for this megaproject was never necessarily whether humans could create reclaimed ground that never moves by a single millimeter. That expectation ignores the basic physics of sand and gravity. The deeper test is whether any ground movement can remain limited, predictable, and entirely compatible with everything built above it. Can the massive network of roads, pipes, and foundations tolerate the inevitable adjustments of the earth below? This returns us directly to the reason ground improvement and vibro-compaction existed in the first place. Engineers knew the ground would move, and they fought to keep that movement within safe limits. Which brings us back to that initial measurement of exactly 5 millimeters. 5 millimeters was never terrifying because it is a large physical distance. It became a warning signal because it raised a fundamental question about scale. We are looking at a tiny movement beneath a huge artificial island that relies on thousands of interconnected systems. Palm Jumeirah does not need to visibly vanish beneath the Gulf for ground movement to matter. The dangerous version of this story simply begins when one part of the ground stops moving in agreement with the part right beside it. Look at the iconic landmark from space today, and it appears completely motionless. That visual contradiction is the final image. Underneath that calm, unified surface, the ground and the infrastructure are locked in a continuous physical negotiation. The survival of an artificial island does not depend on absolute stillness. It depends on the ability of thousands of structural connections to absorb the reality of the ground beneath them. A tiny measurement only matters when it forces a rigid system to bend. This video is for educational and documentary purposes, exploring general geotechnical and structural engineering concepts. The scenarios discussed represent hypothetical engineering mechanisms and do not imply current catastrophic failure at Palm Jumeirah. This content does not constitute professional engineering or real estate advice. What would worry you more, the entire palm moving slightly downward together, or discovering that just one small section was moving differently? Let me know your thoughts in the comments below. Subscribe to the channel for more investigations into the engineering realities of Dubai.